Chapter 21, Podcast 6. So we're going to turn our attention to the fact that there has to be a relationship between our voltage and our Gibbs free energy, because we've seen that negative Gibbs free energy means it's spontaneous, positive voltage means that a reaction is spontaneous. So they have to be tied together somehow. And from our previous thermochemistry chapter, we do know that our Gibbs free energy and our equilibria constant K are related to each other, so thus our voltage and our equilibria constant has to be related to each other as well. So let's see how that all plays out. So we know that if the voltage of a redox reaction is positive, then that reaction is spontaneous. And by definition, all voltaic cell reactions have to be spontaneous redox reactions. So all voltaic cell reactions are always going to have a positive standard voltage. Now, if the voltage of a redox reaction is negative, right, then it has to be non-spontaneous. It's going to be the opposite of that. So if it's positive, it's spontaneous. If it's negative, it's non-spontaneous. Now again, right, for our cases so far, we have only been looking at things that are at standard conditions, right? Our E0 standard, our standard voltage, which means that all of our aqueous solutions have to be 1 molar, and anything that's in the gas phase has to be 1 atmosphere. Now, again, we're going to get into situations when we have things that are not at standard conditions, but for right now, we're going to stick with just at standard conditions. So when we have our standard voltages, right, we know that positive means it's spontaneous. So then, right, how then is that related to our Gibbs free energy and our equilibria constant K? Let's start by looking at the relationship between our standard voltage and our Gibbs free energy change, right? And so there's a relationship between the spontaneity of a reaction, right, and a voltaic cell, because we know that our delta G, a negative delta G, is spontaneous, and a positive standard voltage is spontaneous. And so what we find then is that we have a relationship between those two where our delta G naught is equal to negative N F, all right, E naught. So our delta G, right, that's just the standard free energy, right? So we've calculated that in our thermodynamics chapter previously to this one. Remember, it's standard conditions, so all of our gases are 1 atmosphere and our solutions are 1 molar, just like we're used to. Our E naught is the standard cell voltage, right, that we can calculate that one way or the other as well. Probably one of the most difficult things is called N there. That is the number of moles of electrons that are transferred during the reaction. All right, so what I find is that students really want to take that N and be like, okay, if one half reaction, say, had 6 moles of electrons, and the second one, then for our second half reaction, like if the first one gave away 6 moles of electrons, our second half reaction gained 6 moles of electrons, that means it's 12, right? No. So what we need to do is for N, right, this is the number of electrons in one half reaction, whether that be the reduction half step or the oxidation half step. All we need is the number of moles of electrons from one of those half reactions. So if the reduction has 6 and the oxidation has 6, your N is going to be 6 and not 12. All right, F is the Faraday constant. All right, so F is equal to 9.648 times 10 to the 4th, all right, joules per moles times volts. All right, this is just a constant, so we can plug it in as that number anytime that we need to use this equation. Just so you know, right, I mean, some constants, like our Avogadro's number, 6.022 times 10 to the 23rd, some things like that, or our gas law constants, you're probably going to memorize those. This one we're not going to use often enough for us to have to memorize it. It'll be given to you if you need it. And so don't have to worry about memorizing that for any of your exams or something. It'll definitely be provided when and if we need to use it. Now, we know that our delta G is equal to negative NFE. That's given to us from this chapter, a relationship between delta G and our standard voltage. But let's now take this a little bit step further, and we're going to see then how else we remember delta G being related to other things in previous chapters. Now we're going to look at how our standard voltage and our equilibrium constant K are related to each other. So our delta G naught is equal to negative RT ln of K. All right, this is from chapter 20, right? Thermodynamics, we learned that our delta G is equal to negative RT ln of K. And from the previous slide, right, from this PowerPoint, we learned that our delta G is equal to negative NF E naught. All right, well, if delta G are equal to both of these things, then a negative RT ln of K is equal to a negative NF E naught, and we can make both sides positive. So just like it said here, our RT, natural log of K, is equal to N times the Faraday constant times our E. And so I can then rearrange this and we get that our standard voltage is equal to RT N over NF times the natural log of K. Now my bottom little bullet point says that we can combine RT and F into 0.0257. All right, now what I want to point out is that this is only valid at 25 degrees Celsius. All right, all other temperatures must use RT and F. All right. So here again we have the fact that our E naught is equal to RT over NF times the natural log of K. All right, so R is the 8.3145 joules per mole Kelvin, R. Right, so remember that we're going to use that one. Our temperature in Kelvin. Right, remember that our temperature has to be in Kelvin. And our F for this is going to be our Faraday constant. Right, and our Faraday constant happens to be our 9.648 times 10 to the 4th joules per moles times volts. All right, now again, if our temperature is at 25 degrees Celsius, right, or 298 Kelvin, then, okay, only when that's the case, then RT divided by F is equal to 0.0257 volts. If it's any other temperature, do not use that. If it tells you not to use 0.0257, then don't use it. I only use that like if it's at 25 and there's no specific way of saying, hey, don't use that value. All right, it also says that if E naught is positive, then our K is greater than 1. All right, so the natural log of K out there, right, this part out here, natural log of K. If K is greater than 1, then the ln of K is positive. And so you've got 0.0257 divided by some number of moles of electrons transferred. That has to be a positive value. Times something positive, then that whole thing is positive. So our voltage is positive. If the natural log of K, right? If K is less than 1, then the natural log of K is negative, right? If you don't trust me, try it. Try the natural log of 0.25 or the natural log of 0.5, some number that's less than 1. You're going to get a negative for the natural log of that. So 0.0257 divided by some number of moles of electrons, some positive thing there, times a negative, you're going to get something that is negative. So that's where these two bullet points come from. Right? We're taking an equation, right, but we're manipulating that equation, looking at things about it in order for us to figure out whether something is positive or negative, how those things are related to one another. Time to work sample problem 21-5, which is going to have us go between our equilibrium constant, our standard voltage, and our Gibbs free energy change at standard values. So we are going to start with A, right? And look, they are going to give us for all of these problems that we are at 25 degrees Celsius and that we have an N equal to 4. We'll figure out how to find N a little bit later on, but right now we're just given that value, which makes this a little bit easier because it's one less thing that we have to worry about. Right? It's already in there. All we're going to have to do is plug that value in. So for part A, we're given K. That's the part that's given to us right off the bat is 1.6 times 10 to the minus third. Okay, so what I'm going to do is I'm going to solve for E first, and then I'm going to solve for our delta G. You can do these things in pretty much any order that you like to. I'm just going to go with E first so that we can see that way. But again, if you wanted to solve for delta G first and then solve for E, you could do that, whatever, but we're going to do it this way first. So what I know is the relationship between our E naught and our K is that E naught is equal to, all right, this is at 25 degrees Celsius, so I'm going to say that, right, RT over F is 0.0257 volts divided by N times the natural log of K, or that E naught is equal to 0.0257 volts divided by N, which is 4, that was given to us in the problem, times the natural log of K, 1.6 times 10 to the minus third. All right, so our E naught, right, our standard voltage is going to be equal to negative 0.041 volts. So does that make sense, right? I'm going to ask myself that. So our K was less than 1. 1.6 times 10 to the minus third is a number that is less than 1. So thus we should have a negative voltage, and we did. So that checks out. That makes sense. All right, now let's calculate our delta G naught. So I'm going to say that our delta G naught is equal to negative NF times our standard voltage. So we've got, all right, which is negative 4 moles, right? That's our N is 4 from the problem, times our 9.648 times 10 to the 4th joules per mole times voltages, times volts. And then we're going to multiply that by our standard voltage, which is negative 0.041 volts. So the volts go away, we're going to be left with joules. That sounds okay for delta G, although we usually are going to do our delta G in kilojoules. So our delta G naught is equal to 1.6 times 10 to the 4th joules, or 16 kilojoules. All right, and that's a positive value. Again, does that make sense? All right, well, if it were spontaneous, then our delta G would be negative, but delta G is positive. If it were spontaneous, our voltage would be positive, but it's negative. So they both are saying that this is non-spontaneous. So both of them are agreeing with each other that this is a non-spontaneous reaction. All right, now we can fill out parts B and C on our next slide. Well, continuing on with sample 21-5, part B starts with our standard voltage, and I'm going to use that to once again solve for our delta G, remembering that our delta G naught is equal to negative NFE, which is negative 4 moles of electrons still times our 9.648 times 10 to the 4th. And we are going to then say that it is our E naught is 0.117 volts. Right, that was given to us in the problem there. So our delta G in this case is going to be negative 4.52 times 10 to the 4th joules, which is negative 45.2 kilojoules. All right, so we had a positive voltage, that screams spontaneous. We have a negative delta G, that's also spontaneous, so that looks good. All right, now we're going to solve for K. So I'm going to say that our standard voltage is equal to our 0.0257 over our N, which is 4, times the natural log of K. And K is what we're looking for. So we have a 0.117 volts is equal to 0.0257 over 4 times the natural log of K. I can do all the algebra here. We're going to find that our K then is equal to 8.1 times 10 to the 7th. All right, that value is greater than 1, which makes sense because when we have a positive voltage, our K should have a value that's greater than 1. C, we can basically work the exact same way. What I would say is just make sure that you come up with the same answers for C as are written here in the table. Make sure that you can do that on your own. We have seen us talk about, relating between our equilibria constant and the size of it to whether we're going to end up with mostly products or mostly reactants once we reach equilibria. Talked a little bit about this at the very end of chapter 20 with our Gibbs free energy. Same thing, we can do this with our standard voltages. We just need to know that, again, these are not hard and fast, steady rules with exactly these values. But in general, right, anything where you have a standard voltage that is going to be greater than 0.10, right, positive 0.10, right, it's positive, so it's spontaneous. Well, anything with one that's greater than 0.10, that's usually going to be like mostly products at the end, meaning that our reaction is going to basically go to completion. Right? The opposite is true then if we have, a standard voltage that is less than negative 0.10. Remember, negative standard voltages are non-spontaneous. And so it's not going to really want to go and make very many products if it's non-spontaneous, right? And the larger and larger that voltage, the smaller and smaller, the more negative and more negative that voltage is, right? Then we're going to end up with reactions that are barely going to go and make any products whatsoever. So we're going to be left over with almost all reactants. And then again, like in the middle, anywhere in between those two, right, we're going to have appreciable amounts of both reactants and products once it's all said and done. All right, so that's our relationships between our voltage, our equilibria constant, and our Gibbs free energy. In our next podcast, we're going to see what happens when we're not at standard conditions. How does that change our voltages if we're not at 1 molar for all of our aqueous things, or we're not at 1 atmosphere for any of our gases? How's that going to affect stuff? And will that affect whether our reactions are going to be spontaneous or not?